Next thing we're going to figure out. Why? Because of the percent of the energy of the wave that transmits. It all depends on that. Oh, they did this. You see here? I wish they had a video. It's more film snapshot. How about the opposite now? Now the wave is coming from denser to lighter. So you see now it goes, so transmitted never has phase shift. But now the reflection, no phase shift because this is lighter. It cannot exert enough force to change the direction. You see? Awesome. Okay, nice. So now with that we'll be able to fully answer this question. Okay, so a wave exists in a string. So given that they've already given us the tension of the string, they've given us the equation of the string, right? We can figure out what? We know the K value is 2.4. So let's figure out all the possible the unknowns for this problem. Lambda is equal to 2 pi over 2.4, right? So then we're going to get a bunch of numbers here. That's the wavelength of the wave, 2.618 meters. So then the omega is 2 pi f, and our omega is 3.2. So then the f is going to be our frequency is going to be 5.509 hertz. We could also figure out the period of the wave. .963 hertz, 1.963 seconds. You just invert the frequency to get the period, right? Then what? We can figure out the velocity of the wave, right? How do we figure out the velocity? Well, I could either do omega divided by k or the wavelength times the frequency. But it's probably better to do omega over k because they're not rounded numbers. You know? So it's just omega over k. So the wave is traveling at that speed. What else can I do? I can figure out the original energy of the wave and the power of the wave. Right? The energy of the wave in one wavelength, what was that equation? Half mu a squared omega squared. Remember that the amplitude was square and the frequency was square, but the mass density was mu. And what was the other one? The wavelength, right? The wavelength was not square either. So then the energy is going to be, well, do we know the mu, the mass density? Oh no, we don't know the mu yet, right? We have to calculate that. Well, we know the tension in the string is 15 newtons, right? So velocity is square root of 15 over mu. Tension over the mass density, right? So that's equal to what? Velocity, which we know is 1.33, right? So square both sides and then divide 15 by the square of 1.33. That's going to give you the mass density of the string. 8.438 kilograms per meter. That's a pretty thick string. That's like a huge, thick rope. Okay, so now we put that number here. The amplitude squared, what's the amplitude? Then that's your 1.6, right? The amplitude of the wave is the whatever in front of the sign. The frequency omega is going to be the 3.2. And then the wavelength is going to be 2.618. Okay, put all of that in. Right? So that's the energy of the incoming wave, energy incident, right? And then the power is going to be what? Well, it's just this equation divided by the period, right? Divided by, it's because it's energy over time. Well, when you divide wavelength by period, you get velocity, right? Or what I could do is I could just take I already know the period is 1.96, then I can just take this equation and divide by that. That's the easier way because I don't have to recalculate everything. So then it's just going to be energy over period. $147.50 watts. Okay, now we are told that 70% of the energy of the wave transmits. It kind of makes sense because the other wave at x equals 10 meters, the one on the right, the string changes to a lighter string. So if it's lighter, most of the energy will transmit rather than reflect. Right? So then, given the information, what's going to happen? If it's a lighter string by 1/3 of its mass density and twice the tension, right? So from there, what can I find out? What's the first thing I can find out? If the tension I know and the mass density I know. Right? Yeah, the velocity is going to increase. So what's the tension going to be? The tension is going to be twice the tension, so that means it's tighter even. So that means the tension is going to be 30 newtons. So that means the velocity is going to increase due to the tension, right? And then on top of that, the mass density is 1/3 of its mass density. So that means it's going to be 1/3 of the 8.438. 1/3 of this guy, right? So, oh yeah, it's going to increase by a lot. Okay. Okay, if velocity increases, what happens to its wavelength and frequency? So the equation is V is lambda F, right? So this one increases. What happens to the wavelength? Increases. What happens to its frequency? Oh, that's the other thing I forgot to tell you. The frequency of a wave is independent of the medium that it is in. Right? Just like the frequency of a light wave is independent if it's in air or water. So a red color wave, upon entering in water, will still appear red. Right? So the frequency, how many cycles per second it's going up and down, shouldn't change. Which is why red color looks red no matter what. Yellow looks yellow, right? So this one does not change. So the wavelength, of course, goes up. Okay, then what else happens? How about the period? Does that change? How did we get the period? By inverting the frequency, right? By inverting the frequency. So if the frequency doesn't change, the period doesn't change. So 1.963. So I'm trying to find out every single thing I can about that transmitted wave now. Okay, how about the omega of the transmitted wave? So I should be putting subscripts here. This is the velocity of the transmitted wave, wavelength of the transmitted wave, the period of the transmitted wave, the omega of the transmitted wave. Well, how did we get omega? Omega is just 2 pi f, right? So that doesn't change either. So it's actually omega stays 3.2. Okay? So then what changes then? Omega stays the same, lambda changes, the wavelength changes, the velocity changes. How about the amplitude of the transmitted wave? Does that change? Or is it still 1.6? Well, that has to do with energy too, right? The energy of the wave. How much of the energy of the wave is transmitted into the new string? 70% of the energy, right? So the transmitted energy is going to be 0.7 of the incident energy. You see? So which is going to be 0.7 of this guy, 289. Got it? So then I'm going to set that equal to half the mass density of the transmitted wave, the amplitude of the transmitted wave squared, the frequency of the transmitted wave squared, and the wavelength of the transmitted wave. Got it? So I'm using the equation all over again. That means the energy of the transmitted wave is equal to 70% of the energy of the incoming wave. So then put everything in. What's the mass density of the...
1/3 of the original.
Yeah, so 1/3 of the 8.438. Amplitude of the transmitted wave is what I'm solving for. Frequency of the transmitted wave.
3.2.
Okay. Squared. Wavelength of the transmitted wave. Okay, so for AT. So you can do that right now. Let's try to do it quick before she comes in.
Omega didn't change, right?
No, omega didn't change.
But based on the formula, omega is equal to B times K.
Yeah, remember the omega is the 3.2?
Yeah, which is B times K.
Yeah.
So B changed, right?
Yes, and the K changed.
K also changed.
Because lambda, K is 2 pi over lambda.
Oh, you're right.
Yeah, yeah.
Okay.
Yeah, yeah.
the original amplitude?
Hmm?
Do we even know what the original amplitude was?
The original amplitude, we have it. We wrote it down 1.6, right? 1.6.
I got 1.481.
1.4.
Yeah.
So you see the amplitude went down because only a portion of the wave transmits into the new string. Okay, so now how do we write down the equation of the wave in the transmitted? 1.481 sine of what? Kx. So what's my k? Did k change? Yeah, k did, actually we need to find k, right? K is 2 pi over 6.416. 2 pi over the wavelength. So slightly over 1. Oh, actually slightly under 1, right?
It's 0.979.
Okay, so 0.979 x minus omega is going to be the same thing. Plus, what's the phase angle going to be? Is there any phase shift upon transmission?
No.
No, right? So it was going to be whatever originally it was. Points, was it 6, 7?
Yeah.
Is that it?
Yes.
Okay, now we should come up with the same thing for the reflected wave. Though for reflected wave it's easier because it's reflecting back into the same medium that it already came from, right? So the k is going to be the same, the omega is going to be the same. So what was the original k? 2.4, right? But I'm going to put a plus because it's reflected, so it's going back in the opposite direction, right? How about the phase angle? Is it going from a lighter medium to a heavier? Is the next one heavier or is it lighter?
Lighter.
So in lighter, is there a phase shift?
No.
No, okay. So 0.67, right? How about if it was the opposite, heavy, light to heavy,
Plus
right? I would do plus pi. Now, can you do minus pi? Yeah. Plus pi minus pi is the same thing. Doesn't matter. So if there was a phase shift, you would do plus minus pi and you would get a new number here. But in our case, no phase shift. Okay? So the only thing left to do is find a new amplitude. How do I do that? Well, 30% of the energy is reflected back. So let's do a little energy analysis. With the reflected wave, it's actually easier to even just do something like this and say the mass density is the same for the reflected as the incident, the frequency is the same, the wavelength is the same. Okay? So the only difference is that the reflected wave's energy is 30% of the incident's energy. So basically the amplitude of the reflected wave squared is going to be 0.30 times the incident wave's amplitude squared. 30% of the energy reflects. Right? So then it's going to be AR is square root of 0.3 times 1.6. So whatever portion of the wave, percentage of the wave reflects, you take the square root of that, that gives you the new amplitude. So, so about 0.8?
Yes, 0.876.
Now, once you have this correct equation, you can answer anything about those waves. I can put in the x values and the t values, and then this, and then tell you the displacement of the wave for this transmitted wave and for the reflected wave. In this chapter, make sure you are in radian mode. This has to be all radian, no degrees. Okay. So, okay, with that, we're done with chapter 16. Monday we'll start sound waves. Chapter 17, we should be done by next week for chapter 17. So then after that, you'll have a week. And the following Wednesday after that, test 2, before we go on spring break. Okay, good.